So, in the previous lecture, I talked about the acceleration and velocity. How do we calculate acceleration and velocity? And this, from that, we can calculate the force, that is the centripetal force, in the orthogonal coordinate system. So we concluded that even though the circular motion is uniform, but still then there is a component which produces an acceleration inside the body, and that very acceleration is produced by the force which is called as the centripetal force, and this centripetal force is actually is exerted towards onto the center. Okay, so it is centric. Actually, it is the centric force. It is the centric force, so it's also called as the centripetal force. Now, in this lecture, I'm going to talk about the velocity and acceleration in the plane polar coordinate system. Fine, because it is very much important to deal with the things in physics. We come across the polar coordinates, we come across this particles which move along the circular paths, which are rotating bodies, revolving bodies. So for that, the Cartesian coordinate system is not so much suitable to use. So for that, we have to use the plane polar coordinate system, and how the velocity and acceleration is calculated for those particles, for those systems. I'll give you an idea about that thing. So here we are going to discuss and to calculate velocity and the acceleration in polar coordinate system. For example, as in the previous lecture, I took the particle moving along the circular path with center here, the initial position. It started from here, making an angle at any instant of time with this axis at theta. So this is the theta is the angle traversed by that body with the time, with respect to time. Okay, as the time passes, it traverses this much of theta. And keep this in mind, the radius of the circle is a, and this is the position. This is the position vector. This is the not r. This gives the r component. That is the radial component of that very particle at any instant of time. So this is the axis, that is the radius, that is the radial axis, I can say. So for that, how to calculate the acceleration and velocity of this very particle which is moving along the circular path. Fine, we know that the position vector r at any instant of time, it is given as r is equal to the magnitude of that very vector into its unit vector. That's r and r hat. This r hat is unit vector. And from the previous lecture, you have seen that we took this r, the position vector. This is the position vector of this particle, position vector r, as r a and a multiplied by cosine of I, cosine of theta along I, and sine of theta j. This was the position vector of this very particle at any instant of time. Okay, so from that we can say that this very thing is represented by r. This gives the unit vector r hat. Fine, so this is the position vector of this very particle at any instant of time. So how to calculate first we'll calculate the velocity. Fine, and we know velocity, as I told you earlier, it is the first differentiation of the position vector with respect to time. So that is dr by dt. This is represented as r dot, because r dot means differentiation of position vector with respect to time. So differentiating this very thing with respect to time. So that means we are differentiating r hat with respect to time. Fine. This will be represented. This will be given as, first we will apply here the chain rule, differentiation chain rule. Okay, first we have to differentiate this, keeping this as it is, then plus times differentiation of this, keeping this everything constant. So we will get, or for differentiation of this with respect to time, it will be r dot, this is the magnitude of position vector. Okay, so r dot multiplied by r hat as it is, plus r as it is into the differentiation of r hat with respect to time, that is r hat dot. You have to be very much cautious here. I differentiated first this very thing, keeping this as it is, then plus, keeping this constant, multiplied by differentiation of this very thing with respect to time. Dot represents the differentiation with respect to time, which is the Newtonian representation. Keep it in mind. So here we are getting one thing, we are getting the differentiation of position vector itself. Okay, we are getting the differentiation of unit vector itself. So since with respect to time we are not considering that the Cartesian coordinate system is moving itself, no, we are discussing a particle inside a polar coordinate system. Okay, and I have forgot one thing, this gives the unit vector of theta. Keep that in mind also. I have told you also this in the previous lecture. So here we are getting the differentiation of unit vector. So we have to keep in mind, we are not taking into consideration that the polar coordinate system is itself changing with respect to time. That is the position vector of this very differentiation of this very thing. We have to change it into some other quantity which is calculable here. So for that, what I will do, we have already, we know here r prime from this very thing, r hat is cosine of theta I plus sine of theta along g from this very thing. Okay, now I will differentiate it because we are getting a differentiation with respect to time. I will differentiate this very thing with respect to time. Differentiation of this cosine of theta differentiation is minus sine of theta, and theta differentiation is theta dot along I, plus sine theta differentiation is cosine of theta, and theta dot along g. Fine. So what we will get here, theta get it outside, so minus sine of theta I plus cosine of theta g, and theta dot is outside the brackets. So this very thing I have already told you in the previous lecture, if you remember that. What is that? I have told you this very thing, this is represented here as this, from this very equation. This is theta hat, the position vector, this unit vector theta. Okay, so what we'll get here, this very thing will be equal to theta dot into this very thing is theta hat. So our unit vector dot will be equal to theta dot theta hat. So this will be substituted here. Substituting it here, we will get r doubled r dot will be equal to r dot r hat plus r and r hat dot, that is theta dot theta hat, theta dot theta hat. Fine. So this very thing here, the unit vector is not a function of time. Here the unit vector r hat is function of time. So that's why I converted into the another thing where unit vector is not a function of time. So we don't have to differentiate unit vector with respect to time. So that's why I converted it into something else. Okay, that's simple. This very equation gives the first differentiation of position vector, that is the velocity in polar coordinate system. Okay, polar coordinate system, fine. So now again we have to calculate the velocity. For that we have to double differentiate this very thing. Okay, so to get the acceleration